In the last video we talked about signed and unsigned integers, and I'm sure you remember that with a signed integer, if it is a 0 here, it generates a positive number, and if it is a 1 here, it generates a negative number. So remember, signed integers can either be positive or negative, but we've got this most significant bit here. Okay, so depending on what that is, we can then work out our number. So this example here is -128 plus 1 equals -127. So this is a signed integer, okay, because it's got the most significant bits. Now 2's complement is basically using signed integer, okay, so it's a way of representing negative numbers, and at GCSE level signed integers and 2 complement are basically the same thing, so don't get confused by the language. Where it's slightly different is so far we've been converting from binary to denary. So what if we need to convert from denary to binary? What if we've got a negative denary number and we need to convert it to a 2's complement signed binary number? So what if we use 2's complement to do this, okay? So we use 2's complement to convert from denary to binary, okay, using 2's complement. So let's assume we've got a denary value -12 and we need to convert it to, we need to work out what the binary number of this is, okay? So what we do is we just write it out as if it was a positive 12 number, okay? So 0, 0, 0, 0, 8 plus 4 is 12. So that equals denary plus 12. But we want a minus value, okay? So there are basically, what you do is you flip all of the bits, okay? So if it's a 0 here, we make it a 1. So 0 becomes a 1, 1 becomes a 0. Okay, these are all zeros, get flipped to 1s. Then we need to add 1. Okay, very important to remember that. So now 1 plus 1 is 1, 0. So I put the 0, carry the 1. 1 plus 1 is 1, 0. So I put the 0, carry the 1. Now it's 0 plus 1. Okay, and we're just, these are unchanged. Okay, so we're not adding this and this and this. Don't get confused, okay? We're just adding 1 to the number that we flipped. So this is the number that we've generated. So we can use the system that we've been using up till now to check if it actually is correct. So it's a 1 here. Now this is a signed integer, so we know this is the most significant bit. So -128 plus 64. We know 2 64s in 128, so the answer is we're on -64 now. Plus 32. We know there are 2 32s. In 64, so we know we are now at -32 plus 16, so we know that that is going to get us to -16. Then we've got a 0 here, so we don't have to worry too much about that, and then we have another 1, so it's now plus 4. So 16 plus 4 is -12. Okay, so that proves to us that this signed integer is indeed -12, and that we've converted from denary to binary using 2's complement. Okay, in a moment we are going to do some questions, and you are going to convert a denary number to signed integer binary number using 2's complement. But before we do that, let's just look at a positive denary number. So if we've got a denary number of 7 and we need to know what the signed integer binary number is for that, well, if we do this as we would with an unsigned integer, we know that a signed integer uses a most significant bit with the value 0 in it. So we don't need any fancy tricks to know what the signed integer value is for this positive number. It's only if we are trying to work out a negative denary value. So what is that negative denary value as a signed integer binary number? What is denary minus 7 as a signed integer binary number? Well, we can use 2's complement to do that. Okay, so we take the positive version of denary 7. Okay, so that equals plus 7. And then we flip all the bits. So 1 becomes 0, 0 becomes 1. And then we add 1. And remember, we are not getting confused. We're not adding this top row. We're just adding the stuff in the green box. So 0 plus 1 is 1. There's nothing to carry. So all of this just stays as it is already. Now, we can double check that this is actually denary 7. So let's do that. So let's double check that we have indeed got a signed integer number representing denary minus 7 in binary. So look, we've got 1 here, so that's a good start. Minus 128 plus 64 is minus 64. Okay, minus 64 plus 32 is minus 32. Minus 32 plus 16 is minus 16. Minus 16 plus 8, yes, you guessed it, is indeed minus 8. Okay, minus 8 plus 1, okay, so we're just doing this last bit here now, is indeed minus 7. So that reassures us that this binary number, this signed integer binary number, is indeed the equivalent to denary minus 7. And we've worked this out. We've converted from denary to binary using 2's complement. Right, let's do some questions. Okay, let's do some questions, and these questions are going to be converting from a negative binary denary number to a signed integer binary number using 2's complement. So how do we work out what the binary version of denary minus 32 is? What's minus 32 as a signed integer binary number? Right, I suggest you pause the video at this point and you go through the process of using 2's complement to work out what minus 32 is as a signed integer binary number. Good luck. Well, step 1 is to generate a binary number for plus 32. I made a mistake already. Okay, so not too hard. So that is plus 32, but we want to work out what minus 32 is. So how do we do that? Well, we use 2's complement, and the first step is to flip everything. So 0 becomes a 1, and a 1 becomes a 0. So these are zeros, so these become 1. So then we want to add 1. Now sometimes people become confused and start adding up like these 3 rows. You don't want to do that. You just want to add the stuff in the green box. So 1 plus 1 is 1, 0. So we put down the 0 and we carry the 1. Okay, 1 plus 1 is 1, 0. So put down the 0 and we carry the 1. Okay,
so 1 plus 1 is 1, 0. Put down the 0, carry the 1. 1 plus 1 is 1, 0. Carry the 1. 1 plus
1 is 1, 0. Carry the 1. Okay, we don't have to. It's only 0 plus 1 now, so there's nothing to carry. So we just put the 1 down, and then there's nothing to add now really, because there's no carry. So this is the answer, and it looks about right because a negative number has to start with a 1. So this passes the common sense test, and it finishes with a 0, which suggests it's an even number. So that looks about right. So let's reverse engineer that and check if we got the right answer. So just to make it really easy, I'm going to drag this over the top of our grid. Right, so let's work out if this binary number we've just calculated is actually equivalent to minus 32 denary. So minus 128 plus 64 is minus 64. Minus 64 plus 32 is minus 32. Minus 32, we're going to move along a bit now, plus nothing. We don't have anything more to add. So this is our answer, minus 32, and shock, horror, this matches up with what we were trying to do. So we've used 2's complement to quickly convert from a negative denary number to a signed integer binary number. Okay, let's do a couple more, but quickly. So what is the denary minus 25? So how do we work out what denary minus 25 is as a binary number? We use 2's complement. So you work out what plus 25 is as a binary number, and then you flip the bits, and then you add 1, and that gives you your signed integer binary number equivalent to denary minus 25. So pause the video now and work out how to do that. Okay, let's see if I can do it. Anything's possible. So let's work out what 25 is as a positive binary number. So 16, oh, made a mistake already. So 16 plus 4 would be 20, that would be 23, so this gives us 16 plus 8 is 24, that gives us 25. So this is positive 25, remember, not negative 25. So now we need to flip all the bits. So 1 becomes a 0, 0 becomes a 1, okay, so we've flipped our bits now, so now we need to add 1. Okay, and remember we're only adding the stuff in the green box. So 0 plus 1 is 1. 1 plus, well, there's nothing to carry, so this all just carries on unchanged, nice and easy. Okay, common sense, so it's starting with a MSB of 1, so it is a negative number, and it's finishing with a 1, so that is suggesting it's an odd number. So now we can reverse engineer it. So this is our answer, okay? This is our answer. But if we want, we can now reverse engineer it just to check that we've got the right answer. So I've dragged it into the box. So let's double check this is actually equivalent to denary minus 25. So the most significant bit is minus 128, plus 64 is minus 64, plus 32 is minus 32. Okay, so we go from minus 32 plus 4. Okay, so minus 32 plus 4 is equal to minus 28. Minus 28 plus 2 is minus 26. Minus 26 plus 1 is minus 25. So having reverse engineered this, we can confirm that this is indeed minus 25 as a signed integer binary number. Okay, let's do another one. So we've only got 8 bits, so let's work out what denary minus 150 is as a 8-bit signed integer binary number. Okay, now this is actually, don't pause it, this is actually a trick question, because what is the highest number, what's the highest negative number that we can generate with 8 bits? So what's the highest negative binary number we can generate with 8 bits signed integers? So here we go. It's got to be, we'll start with a 1, hasn't it? And if we don't do anything else, if we don't add anything, we've got minus 128. So minus 128 is the highest negative number that we can generate. If I add anything, if I take away any of these zeros, so if I do that number here, it's minus 128 plus 1, which equals minus 127. So with 8 bits, the highest number that we can generate is minus 128. So we can't work out minus 150 with only 8 bits. We would need to use more bits, 16 bits for example. We don't need to do that, that's kind of beyond what we need to know. So let's do another sum. Yeah, let's get rid of this 150. That was a mean question. So what if we said that we needed to work out what the signed integer binary value for minus 100 was? Denary minus 100, what is that as a signed integer binary number? Okay, so remember, you need to work it out as a positive binary number, and then you flip the bits and then you add 1. So pause the video and do that now. Okay, have you got an answer? Let's work it out. So what is positive 100? So it's not going to be that. So 64 plus 32 is going to be 96. So we need that. And then we basically want to add 4. And that gives us a value for plus 100. Okay, so 64 plus 32 is 96, plus 4 is 100. So then we flip the bits, and now we need to add 1. Okay, so here you can see I've added 1 and worked out what I think the answer should be. So let's now reverse engineer it to see if the answer is correct. Okay, so here we have our answer reverse engineered. So we started off with minus 128. And then we added 16, so minus 128 plus 16 is minus 112, and we needed to add 8 to that, which gave us minus 104, and then we added 4 to that, which gave us 100. So the answer was correct. That is indeed the 2's complement signed integer 8-digit number representing denary 100. Okay, let's do one more. Can you tell me what denary minus 53 is as a signed integer 8-bit binary number? Pause the video and work it out. Okay, let's work out the answer. So we can see that 32 plus 16 is 48, 52, 53. So that is the positive for 53. So here we can see I flipped the bits and now we need to add 1. And here's our answer. And now we can reverse engineer it just to double check that it is denary minus 53. So here we can see that it has worked out correctly. We've got minus 128 plus 64 equals minus 164. We add 8 to that. So if we added 10 to that, it would be minus 54, but it's minus 8, so that's minus 56. And then we add 2 to that, which gives us minus 54, and we add 1 to that, which gives us minus 53. So that's very reassuring. We know that this is the signed integer 8-bit binary value for denary minus 153. Let's do one more. Can you tell me what the denary value minus 109 is as a signed integer 8-bit negative binary number, and can you show your working using 2's complement? Pause the video and do it now. So this is the positive binary number for denary 109. So 64 plus 32 is 96. 96 plus 8 is 104. 104 plus 4 is 108. Okay, so now we have flipped the bits, and the next step is to add 1. And here we have our answer. So let's now double check our answer is correct by reverse engineering it. So here we go, it's looking good. So we started off with a 1 here, so that gives us the starting point of minus 128, and then we needed to add 16, which gave us minus 112, and then we needed to add 4, which gave us minus 108. So I've made a mistake, have I not? So it's actually a great revision technique to actually spot errors. So I should have known straight away that this was wrong because it finishes with an odd number here. It finishes with a 0 here, and yet we are trying to generate an odd number. So that is definitely not right. So this is where I went wrong. Right at the beginning, when I was working out what the positive binary value for 109 was, I worked out the positive binary value for 108 for some reason. So all I needed to do was to count properly and work out what the value for 109 was. You probably spotted that, didn't you? So now I'll try again. I've flipped the bits, and now I'm going to add 1. So that's my answer. Now, given my previous track record, we should probably reverse engineer it to check it's right. Okay, so finally we got there.